Hello everybody, in this video we're going to be looking at the change problem and we're going to be looking at the dynamic programming solution to it. The change problem is we have some money, I'll say 10 cents, and we have a bunch of coins, so 1 cent coin, 3 cent coins, 4 cent coins, and we want to make 10 cents using these coins, using as few coins as possible. Basically what we're going to do is we're going to be building up this array, this min num coins array here, and we want to return value number 10 because let's say at value, for example here, value 9, that represents the minimum number of coins to make 9 cents. Value 7, this is the minimum number of coins to make 7 cents. And then, of course, at value 10, which is what we're looking for, because our input was 10, we're going to return this value, which is the minimum number of coins needed to make 10 cents. So we're going to follow this dynamic programming approach and fill in this table. So to begin with, min num coin 0 is equal to 0. Great. For m goes from 1 to money, right? So 1 to money. So m is like this little index variable that we have. So I'll just have a little pointer here. This is m. And m is the value we're going to currently look at. We're going to try to find the minimum number of coins needed to make 1 cent here. So we can clearly see that's going to be 1, right? You need one 1 cent coin. But let's see what the algorithm tells us to make this true. So basically this is saying for each coin, this section here is just saying for each coin, if m is greater than, if the value that we're currently looking for is greater than or equal to the value of the coin, which is only true for coin 1, because otherwise the coin values are bigger, then we make this temporary variable called num coins, which is like how many of those coins we need, how many of these coins we need to make this 1 cent here. And that value is going to be the min number of coins of m minus 1. M is 1 coin. We're looking at coin 1 right now. So that's going to be min num coins 0. Basically what we're saying is we need 1 additional coin compared to whatever value was stored here, because we have a 1 cent coin, right? Since we have a 1 cent coin, we can just move 1 forward. Whatever value was here, we add 1 to it. So this is going to be a 1 based on that fact. Well, in a second, actually. So num coins is going to be 1. And then we just check that we've actually improved. So I kind of skipped over it, but basically you assume there's kind of infinite values in all of these at first. So it definitely has improved from infinity to 1. This is just checking if we've improved. And if so, then you set that value. And now we check the rest of the coins, but the rest of the coins all fail this condition here, right? Because this is larger. 3 is larger than m, 4 is larger than m. We can't subtract, we can't go back 3 cents because we go into the negatives there and that doesn't make sense. So we're done with m equals 1. So now what we do is we just move on, m equals 2. We're going to fill in the next one. Okay. So remember, we have a 1 cent coin, we have a 3 cent coin, we have a 4 cent coin, right? So again, since we have a 1 cent coin, basically what this algorithm is telling us is saying that our possible value here is taking this 1 cent coin, but you're going backwards by 1. So he's saying that I can just add 1 of these 1 cent coins compared to my previous one, compared to the element that's 1 cent away. So yeah, I can put a 2 here. And again, we have this situation where 3 and 4 are the denominations are just too big. So we can't make, we can't use those coins yet. But the next run around is going to be different. The next run around here, we're at 3. And we just go through each coin here and we say, okay, 1. So I have a 1 cent coin. So that means that I can just add 1 to the value from our previous square here. So maybe this is going to be a 3. But then I can now move on to the next coin, 3. Okay, that means I can add 1 to whatever value was 3 away. Because I have a 3 cent coin, so I can just take whatever the value was here. 3 away is adding that 3 cent coin. 0 plus 1 is 1. That's better. That's an improvement. Remember, this condition here checks that we're actually improving. And then for the 4 cent coin, it's too big, so we can't. Now m equals 3. M equals 4. So again, for each coin, we just say, so for coin number 1, looking at I can go back 1. That's what I'm trying to say. I can go back 1 and just add 1 to it. So this would be a 2. Using the 3, I can go back 3, add 1 to it. Again, would be a 2. Using the 4, I can go back 4, add 1 to it. 0 plus 1 is 1. That's an improvement. So the actual minimum value there is 1. We only need 1 coin to get 4 cents because we have a 4 cent coin. For 5, what we do next one. Again, I can just take the previous one for the coin number 1. That means I can go back 1 and add 1 to it, so that'd be a 2. For the 3-cent coin means I can go back 3 places, add 1 to it. That would be a 3. That's not an improvement. The 4-cent coin means I can go back 4 places, 1, 2, 3, 4, add 1 to it. That also gives me a 2. So there's 2 ways, basically, that we can get 5 cents using 2 coins. Right? We can do 4 and a 1, and 4 and a 1. No, there's only one way. Okay, I guess that's it. So because I said here I can go back 1. Oh yeah, 4 and a 1 and a 1 and a 4. There you go. That's the 2 ways. You can either do 4 and a 1 or a 1 and a 4. Those are the 2 possible methods, and so we just saw those both here. Anyways, that's beside the point. Continuing on, hopefully you see the pattern. For this coin, we can either go back 1, we can go back 3, or we can go back 4. Whatever gives us the best value. So I'm going to go back 1. That's a 2. Add 1 puts a 3 here. I'm going to go back 3 now. 1, 2, 3. That's a 1. Add 1, that's a 2. That's an improvement. I'm going to put that there. Looking at 4, I'm going to go back 4. 1, 2, 3, 4. That's a 2. Adding 1, I have a 3. That's a 3. So not an improvement. So 2. We need 2 coins to get 6. 7 is going to be... Whoops. 7 is going to be... go back 1. That's a 3. Go back 3. Add 1. That's a 2. So the reason I'm adding 1 is because I'm using 1 additional coin compared to this, right? 7 cents is nothing but 4 cents plus a coin, a 3-cent coin. I can go back 4. That's a 1. Add a 1. That's a 2. No improvement. So it's a 2. We still need 2 coins to get 7. Almost done. For m equals 8, I can go back 1. It's a 2. Add 1 is a 3. I can go back 3. It's a 2, add 1, it's a 3, no improvement. I can go back 4, it's a 1, add 1, it's a 2. So I only need 2 coins to get 8, I need 2 4s. For 9, you get the picture. Move 1 forward, it's a 3. Move back 3, it's a 2 plus 1 is a 3, no improvement. Move back 4, it's a 2 plus 3, plus 1 I mean, is 3, no improvement. We need 3 coins to get a 9, no way around that. Then finally, for 10, which is what our actual solution is, we can go back 1. That's a 3 plus 1 is a 4. We can go back 3. That's a 2 plus 1 is a 3. That's an improvement. You can go back 4. 1, 2, 3, 4. That's a 2 plus 1 is a 3. No improvement. So it looks like we need 3 coins to get... we need 3 coins to get 10 cents here. And that would be whatever we backtrack to get us that optimal solution. So it could either be going back 4, 1, 2, 3, 4. So I need a 4-cent coin. Whatever got us 2 here. So probably going back 3. So a 3-cent coin. 1, 2, 3. So a 4-cent coin, a 3-cent coin, and then whatever got us a 1 here, which is going back 4. 1, 2, 3. Or 3. Going back 3. Sorry. So a 3-cent coin, a 3-cent coin, and a 4-cent coin is what our optimal solution is. But the algorithm mainly is telling you what that number is, how many coins you need. Minimum number of coins. So hopefully that made sense. It's a little bit hard to put into words, but hopefully you see the pattern where you just kind of, at your value, you just kind of keep going back for each denomination you have. Except at the start, you don't want to go into the negative, so it doesn't count if you go into the... Okay, that's all for this video.